All right, let's do 2.3. So reminder, this document is under note guides on Google Classroom if you want to print it out, but you are welcome to write your own notes as well. And I do expect you to still watch the videos in Apex, and this video that I'm making is just to supplement that. So in 2.3, we're going to determine if a data set is normal using some different methods. We've already talked about normal data sets. We've talked about how a normal distribution is symmetric and bell-shaped. And so we can determine if a data set is normal simply by looking at that distribution and generalizing. In this case, we're going to go ahead and talk about some more specific ways that we can verify that a data set truly is normal and not just symmetrical some other way. So there's two basic ways that we're going to check it. We're going to use the empirical rule, which we talked about before, and we're going to use something called a normal probability plot or a normal quantile plot. So starting with the empirical rule, we talked about the empirical rule before. That was 68, 95, 99.7, which refers to the proportion of data that is either 1, 2, or 3 standard deviations away from the mean in a normal distribution. So again, with a truly normal distribution that is symmetric and bell-shaped, the mean is going to be right in the center. And if I measure 1 standard deviation to the right and to the left, the empirical rule says the amount of data between those 2 standard deviations is going to be about 68% of all of the data. And then if I move it over again and I move 2 standard deviations below the mean and 2 standard deviations above the mean, that total data is about 95% of what we have. And if we move again out 3 standard deviations below the mean and 3 standard deviations above the mean, we now have about 99.7% of the data. So we can use that empirical rule when we're given a data set to determine whether or not that data set is truly normal. Because just because it appears to be symmetrical and bell-shaped does not necessarily mean that it's going to be normal. So we want to be extra sure here. So the first thing is that we want the empirical rule to apply. So let's look at this distribution here. It says we're given a distribution with a mean of 45 and a standard deviation of 3. And the population size is 150. So we have 150 individuals. The average, whatever variable we're looking at, is 45. And the standard deviation from that mean is about 3. So we're going to expect that 68, getting ahead of myself, 68% of the data is going to be 1 standard deviation away from the mean. So what is 68% of the data? Well, what is 68% of 150? We know there's 150 individuals. So to get that total, I'll take 0.68 and multiply it by the total of 150, which gives me 102. So 68% of the data, or 102 individuals, need to be within 1 standard deviation of the mean. So I take my mean, 45, subtract the standard deviation, and take my mean, 45, add 1 standard deviation, and I get those boundaries. So if our distribution here is truly normal, then about 102 individuals from the set of 150 should have a value between 42 and 48. Okay, continuing here, what about 2 standard deviations away from the mean? What about the next number in the empirical rule? Let's look at 95. What is 95% of the data here? Again, we can calculate that. 95% of the data, there's 150 individuals, we know that, we've pulled that. So I take 0.95 and multiply it by 150 and find that there would be about 142.5 individuals. And I could write that there, but I mean, in reality, we can't have half an individual, so you could round up. About 143 individuals should be in that 95%. So again, if this data is normally distributed, then we're going to expect 143 individuals, which is 95% of the data, to have a value that is 2 standard deviations away from the mean. So I take my mean again, and now I'm going to subtract 2 standard deviations, or 6, which gives me 39. And then I do the same thing to find the upper bound. Take my mean and add 2 standard deviations, or 6, which gives me 51. So now, again, we expect, if this is truly normal, that 143 out of 150 individuals, which is 95%, will have a value between 39 and 41. And we can, again, apply this again to the last part of the empirical rule, 99.7. What is 99.7% of the data? Again, we're told there's 150 individuals. So take 997 and multiply it by 150. 99.7% of the data should consist of 149.55 individuals. I'll go ahead and round it up to exactly 150 individuals. So we want that 99.7, or that 150 individuals, to have a value that is within 3 standard deviations of the mean. So again, I say, here's the mean, subtract 3 standard deviations. That's subtract 9. That gives me, 30, not 50, 36. Take the mean again and add 3 standard deviations, or 9, and we get 54. So again, if this is truly normal, then we expect that about 99% of the data, or about 150 out of 150 individuals, will be between 36 and 54. So that's one way that we can test to see if things are normal. Is it possible for a distribution to be close to normal but not actually normal? Absolutely. There will be some variation with this, and that just means that the properties of normal curves that we apply are going to differ a little bit. They might not always work perfectly because there's going to be some variation here. The last thing that we need to know is that the standard deviation, given the empirical rule, which says that 99% of the data is within 1, 2, 3 this direction, standard deviations that direction, and 1, 2, 3 standard deviations that direction. That's a total of 1, 2, 3, 4, 5, 6 standard deviations can make up 99.7% of the data. So if we wanted to approximate the standard deviation, we could actually say, if we know it's normal, the standard deviation should be about 1/6 of the total range. So the range, remember, is the maximum minus the minimum. So if I know the range is 50, meaning there's 50 individuals between the minimum and the maximum value, or there's 50 points between the minimum and the maximum value, then 1/6 of that should be about equal to the standard deviation, so that the empirical rule can apply. Okay, so again, that's one way that we can make sure that our data is truly normal. The next tool that we have is called a normal quantile plot, also called a normal probability plot. A normal quantile plot, or a normal probability plot, is a type of dot plot. And this dot plot displays the z-scores on the y-axis in terms of the actual raw data, the raw scores, the x scores. And what we end up with is a plot that looks like this one here. It's a dot plot where we have our z-scores on the y-axis and our X values are raw data on the X-axis. And so you can see here, this normal probability plot is not bell-shaped it's not bell-shaped. It's not like the curves that we've seen before. If a normal quantile or a normal probability plot for the data is approximately linear, like it is here, then the distribution is normal. The closer to a perfect line this dot plot is, the closer to a perfect normal curve. We can see there's a little bit of variation in here. It's not perfectly linear, so it's not perfectly normal. But the closer that this plot gets to a perfectly straight line, the closer it is to a perfect normal curve. So in this one, we can say this distribution is approximately normal because our normal probability plot is approximately linear. And it appears there might be a little bit of a tail on the right side. So let's see for the different variations of these normal quantile plots or these normal probability plots. So as I said before, a perfectly normal distribution that is symmetrical and bell-shaped and follows the empirical rule is going to have a probability plot or a quantile plot that is perfectly linear. And you can see here, that is the case. They form a perfect straight line. As we move to a skewed distribution, right and left, you can see how that changes. When we're skewed right, meaning I have a tail on the right, you can see that the data increases very quickly on the right end, and I have these spread out dots here. When we're skewed on the left, we have the opposite. I have very spread out, sharply increasing data points over here on the left side. So you'll be asked, given a probability plot or a quantile plot, whether or not something is skewed right, skewed left, normal, or other. You can see these two kind of in the middle there. They're almost normal and just maybe a little bit skewed. Same thing here. This is almost normal and a little bit skewed. And if you look at their graphs, they're pretty close to normal. There's a little bit of a tail right there, and there's a little bit of a tail right there on that one. But I think that that's close enough that we could probably treat it as a normal curve. Another one that they didn't point out here actually is the uniform distribution. The uniform distribution, remember, is symmetrical, but it really doesn't have a shape at all. It's just kind of like across the board, all the same frequency. In the normal probability plot, that one's going to be kind of S-shaped. It's going to do both skews. Okay, but we probably won't see that one as much. So it is possible for the normal probability plot to be either linear or curved. Okay, we want the normal probability plot or the quantile plot to be linear, but that does not necessarily mean that it's always going to be linear. So the next thing we want to do is we want to practice actually doing this with a graphing calculator. So I have a data set here, and this is from the Apex practice. I have this data set here that we're going to create a normal probability plot for to see if it is normal using a graphing calculator. The very first thing we need to do is put this into the list in our calculator. So remember, to do that, you're going to turn your calculator on, click the Stat button, and then choose option 1, Edit. If you need to clear out an existing list from your calculator, remember you can go up and highlight the L1 and hit Clear, Enter. And that will clear the entire list at once for you. After you have that cleared out, go ahead and put in these data points with me and see if you can get what I have. All right, so here I have all my data put into my calculator, and I can tell that I have all the pieces that I need because now that I'm at the very bottom, it says I'm on my 51st term, and from the table I can tell there are 50 terms. I can always scroll up and down and double check that I have the right things in here, and I can use the delete button here or the insert button, which is shift delete, to make corrections if I need to. Now that I have that all in there, I'm going to go ahead and make my normal probability plot, also called the normal quantile plot. So the first thing I want to do is I want to double check that there's not already something graphed in my calculator because it's going to throw things off. I'm going to go to my y equals and double check that there's nothing in there. If there is, I would clear it out. And now I'm going to go to my stat plots by hitting second stat plot and make sure that all of my stat plots are off besides the one I want to work with. So if I need to, I can go scroll through and turn those off, or go to option 4 and turn them all off at the same time. So I'm going to go to stat plot 1, and I'm going to make my screen look like this. I'm going to turn it on, which it already is on, and I'm going to choose the last type here, which looks like that. When I choose that, I get some new options. It asks where I want my data to come from, and I want it to come from list 1. That's where we put it. And where do I want my data axis to be? We already said before, with our normal quantile plots, our x values are on the x-axis, and my y-axis will actually be z-scores. So we're going to choose x, and that's probably what's already selected for you. So after that looks like that, I'm going to go ahead and graph this. And when I graph it, I might need to adjust my window to see what I need to see. And actually, I don't see anything right here, so I definitely need to adjust the window. The best way to adjust your window anytime you're making any kind of a plot in statistics is to click this zoom button and choose option 9, which is zoom stat. And you can really just click that 9 button or scroll down and hit enter. So I'm just going to click 9. And it should automatically zoom into the best view of my probability plot. And there it is. So, is this distribution normal? How can we tell? So I would say yes, this distribution is approximately normal because there's a little bit of a variation from a perfect line right over here, but it's close enough to a line that I can say yes, this is definitely going to be treated as a normal distribution. So let's go back and put that in our notes. Is this distribution normal? How can we tell? Yes, the distribution is approximately normal. Because the normal quantile plot, or normal probability plot, same thing, is approximately linear. And that's it.